Okay, talking about secants today and the angles that they form. We have chosen properties we know about those secants. Tangents can be involved a little bit, and we'll talk about angles and lengths, but for this video it's just going to be secants and their angles. So what is a secant? It's a line that goes through a circle. You might say, haven't we done that? Well, a chord is part of a secant, but a chord is just a line segment. Secant goes all the way through. I will note that these properties do work for just chords as well. But you'll notice on some of these, when the lines go outside a circle, they have to be secants. There's two theorems. The first one is that for any random angle inside a circle. Notice that this is not a central angle. There's no dot signifying the center. So it's a random angle on the inside. If I outline the intersecting lines, X is the arc that angle 1 goes to. We're also going to need angle 1's vertical angle, and Y is the arc that it goes to. All right, with that setup, the measure of that angle, angle 1, the measure of that angle formed by two intersecting lines that intersect inside a circle is half the sum. Sum being plus, half the sum of the intersected arcs. So over here we have X plus Y. X is the red arc, Y is the blue arc, half of the sum. In other words, it's just an average. Okay, so in other words, it's just an average. Okay. We are going to prove this one. Let me redraw this figure because I want to kind of make it a little bit bigger. And I'm going to call this point down here A, this B, this C, and this D. And we don't know that's the center. It could be. All right, let's prove why this one's true. So let's assume we got statements and reasons. And what we have over here is just the circle. I'm going to say with intersecting chords or secants. I guess over there, well, no, there are secants. Intersecting secants. AC and BD. By what I named them. Now you should think this looks fairly similar to what we did before with inscribed angles, right? What's similar? Because inscribed angles were half the arc. This one is half the sum. So what I'm going to do is use inscribed angles here in a second, and that's going to help us figure this out. There's another thing I need to do, and I'm going to create, let's see if I want to do that first. I do. I'm going to create another segment in here. I'm going to draw an AD. Basically what I'm doing is I'm making a triangle at the bottom here, that triangle. And I'm going to use a property of triangles, and I'm going to do inscribed angles. Okay, so here's what I'm going to do. I'm going to do each of these angles down here, like angle BDA and CAD. Okay, I'm going to use the inscribed angle theorem. Because, I mean, look at this, X and Y. According to Y column, this is X and this is Y. So I need to get BA and CD involved. So I'm going to use inscribed angle theorem to help me out with that. Because the measure of angle A is half. Let's see. Yeah, I was going to CAD. I guess I'll keep it as A. That's fine. Yeah, let's do. Sorry. Let's do CAD. It's half the measure of arc CD, or I guess I could just say Y. I think it was CD. At the same time, so that was kind of angle A. So now we'll look at angle D, angle BDA. The measure of angle BDA it's an inscribed angle as well. It's half X, or half, I'll put BA. Half the measure of arc BA. That's just the inscribed angle theorem. The reason I did that, I wanted to get BA and CD, in other words, X and Y. I wanted to get them involved. Okay, and now I need to get angle 1 involved. And there's something we know, so here's a triangle, something back in Unit 3 with triangles. This is a type of angle from that triangle. It's an exterior angle. There was a theorem that said that exterior angle is equal to the sum of these two remote interior angles. So I actually know the measure of angle 1 is equal to the measure, it's the 2 from part 2, the measure of angle CAD plus the measure of angle BEA. Again, that was called the exterior angle theorem. That's from Unit 3 of triangles, exterior angle theorem. That's good because I needed angle 1 and I needed these arcs. And hopefully you can see where we're going with this. I can now plug these in. So I'm just taking equation 3, plugging in CAD. Well, that's half the measure of our CD. Just do a little substitution. Plus, well, BDA is right here, half the measure of arc BA. So I just plug those in. Just substitution property. And finally, to finish off this theorem, all I need to do is factor that out. Factor out a half. And I'll be left with the measure of arc CD plus the measure of arc BA. Factoring out in GCF is distributive. Go in the opposite direction, we distribute that. Okay, nice little proof there. There's going to be a second theorem I'm not going to show, but that first one is I think the most commonly used one with these secants. Let me move on and talk about the second theorem, and then we'll do some examples. The second theorem is what if the angle is outside? So if we have two secants, or well, here, no, you got to have at least you have to have some secants or a tangent outside a circle. Measure that angle formed by two lines that intersect outside a circle is half the difference of the intersected arcs. Difference with numbers or angles is subtraction. Similar formula, just a minus. Angle 1 is outside the circle. It's formed by two secants. It could, I should note, it could be two tangents. This formula also works. Or it could be one tangent and one secant. Okay, so it works in any case. And it's going to be half the difference of x and y. X is the outside arc, y is the inside. It's always, x is going to be the bigger one. Because you're moving further towards the circle, the angle is getting bigger, x will always be bigger. It's always a bigger number minus the smaller, outside minus inside. Okay, here's some examples. In A, now really the progression, I'd say, you should look for it in this, what we've done so far. Do you have a central angle? So for example, I'm looking at A. Nope, it has to be coming from here. Do we have an inscribed angle? Nope, it has to be like an angle like that, vertex on the circle. Okay, so neither of those. Then an angle inside, just a random angle inside. Nope. Don't really have that. Have a diameter. And then angle outside, which we do have. So that's kind of the progression you should look at. Central angles are the easiest, inscribed is next, and then these two. So I do have an angle outside. X is the angle. It's going to be half the difference of the two arcs. I should outline the angle first. Notice the angle, it really makes two arcs. This is a case that has one secant and one tangent. It makes the 45, that's the inside one. And the outer one, well, this was a diameter here. And so that's a semicircle, and I can subtract the 45 from 180 to get 135 for this arc. So we have half of 90, which is 45. By the way, it's just a coincidence that it's the same as this inner arc. That will not always be the case. Let's get rid of that. Okay, so for B, no central angle. That is not, there's no center dot indicating the center. So there's no central angle, there's no inscribed angle either. There's an angle inside the 35. So I'm using the top theorem that angle is half the the sum of the two arcs. Now the two arcs are 30 plus the other arc is x. That goes here. This 35 is the angle measured. So that's going to go here. I'm going to get rid of that, put in 35. You could distribute the half and work it out. I like to clear the denominator by multiplying both sides by 2. Both methods will work fine. You get 70 equals 30 plus x. You subtract 30 to get 40. Now, since the first formula here about the sum is actually an average, adding up two numbers divided by 2 is an average, you could have also just reasoned through saying 30 plus 5 gets me 35, plus 5 again gets me 40. That works. I mean, you can also check your answers. 40 plus 30 is 70, and half of that is 35. On C, the measure of angle 5. It is not a central angle. It is not an inscribed angle. It is an angle inside the circle. Notice that angle 5 goes to these two arcs in red. So the measure of angle 5 is going to be half the sum of the red arcs. I'm writing sum and I'm writing plus for a reason. We're not going to be able to find those arcs individually right now. However, we don't need to. We just need the sum. And notice that everything else here, the 150 and the 110, makes up the whole circle between the green and the red. So if I add 150 and 110, I get 260. And if we subtract that from 360, we get that there's 100 left between these two arcs. And that's all I need. I don't need the individual arcs. So angle 5 is 50. Yeah, you can have individual arcs, that's fine. That can help too, but you don't need them. So actually here we won't be able to find the individual ones. Now there's another way to do this. Sometimes I've seen this where students will call this angle 1. By the way, I like this method as well. Call this, or let's say x. Call this some other angle. So we're trying to find x. X is an angle inside. It's half the sum of 110 and 150. That would be half of 260, so x will be 130. So you can find x being 130, and then you can note that 5, angle 5 and your x are a straight line, they're a linear pair, and so they're supplementary. So you can just do 180 minus 130 to get angle 5 is 50. Just an alternate method on that one. All right, finally D. There's no central angle, no inscribed angle, no random angle on the inside, but there is an angle on the outside. And here's the formula. The angle, 25, is half the difference of the two arcs that it intercepts. Outer minus inner. 90 is outer, minus inner, 5x. Okay, you could distribute if you want. Well, let's do that on this one. 25 equals 45 minus 2.5x. Subtracting 45, we get negative 20 equals negative 2.5x. And divide by negative 2.5, we get 8. You would have gotten, if you multiplied by 2, you would have gotten 50 equals 90 minus 5x. They're the same. Subtract 90, negative